other thing, like there's like different probabilities. So not only is everything quantized, but there's different like probability states. Like it's a little confusing how it all works together, but yeah.
I thought it was a uncertainty in position.
Yeah, you're right. You're right. That's right. So the uncertainty position is also related to the wavelength. So you're correct. Oh, you can't see it here. But this is something that's cool. So it's just basically atom with different electron shells. So one of the first experiments that like prove the quantum nature of reality is the photoelectric effect. Does anyone know what the photoelectric effect is?
I think it's light particles were bombarding a metal and it ejects electrons from that metal.
Exactly. So like what was really interesting is that they had this metal, right? And let's say they had red light, which has a longer wavelength, right? So they're shining red light on this metal, and like even if they shine a whole bunch of red light on this metal, no electrons are being escaped. But when they shine, even if they have blue light, which is a higher frequency, and even if they just shine a couple blue lights, like electrons are being released. So this basically Einstein came up with the idea, oh, there's photons, where like instead of light just being this wave, no, light's in discrete particles, and the energy of the photon is related to its frequency. So like, even if you have a whole bunch of red photons, they're never gonna have enough energy to make the electron leave its orbital state. You're gonna need a blue photon. And that's basically how solar cells work. But like, using the photoelectric effect. But basically what this shows is that photons are quantized units of energy. And not only that, but the different electron orbitals are quantized. Like, it takes a certain amount of energy to get to the next level. Like, if you don't have the energy, it's not going to move. So there's these different states. Instead of this like gradient, you know, we can just move everything like, oh, I can move this here, or I can move this here, or move here, right? But with electron, you can only move it like here or here. There's absolutely no in-between state. It's only one or the other state. And then each state has its own probability, which is kind of like what we're talking about here. And so it's probable for this electron to exist in this state, just for 1 second, but it'll most likely be in this, like if it's most likely in this state. And then when you give enough energy, like it'll most likely be in this state's probability. But there's a small probability that it can just be anywhere. So there's these different states, and they're related to the harmonics of wave frequencies that I was talking about in the patterns of nature. Like these are different like harmonics, right? And these probability fields are based upon waves using Schrodinger's equation. So this is like a particle in the box. So like one wave state is for it to be like mostly here, and this is like a density. So the blue is like higher density, or it can be kind of like here. Is this kind of like harmonics? You know, it can be here or like double or triple, right? And each one of these has its own probability. So this is the most probable, and then these are less and less probable. And the way that you get its average position is like you sum up each probability state times the probability of that. So it's like this is most probable, this is least, and then when you add them all up, it's probably going to be mostly like this. So probability fields are really, really interesting. They're one of the most like complex and like intriguing parts of physics. So I want to show a little video on it. So hopefully you guys, it's kind of a little dumb video.
We first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. And we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay. So that's a very cool, inspiring video. I like it, but sometimes things can be a little confused by it. That the observer, as in a conscious observer, collapses the wave field. But so why do you guys think that it acted differently when the observer observed the particle?
Because doesn't the observer need to bounce light off the electrons, and then the photons can actually interact with the...
That's exactly correct. You would have got an extra point on the job.
But won't there be light bouncing off whether there's an observer or not?
Yeah, I think they do it in a vacuum chamber, so there's no interaction.
So there's only light when they decide to look at it?
There's only light when they decide to look at it.
Can you kind of further explain
Yeah,
what
explain.
I just said a little bit?
Yeah. So going off what you said, see the observation only happens. The only way to observe a particle is to bounce light off of it or another particle. So like if there's like this electron, right, it's existing as a potential, it can be anywhere, it's a probability field, right? It doesn't, this is like where it's most likely going to be, but it's really more like a cloud. But then if I have a light coming in, it's like, where really is it? I want to like look at it. When the light comes, it's going to interact at one point and it defines it at that point. It collapses the probability field at that point. And then you can get information about it. So, yeah. So it's really interesting. It's basically, yeah.
So you're saying lights, like when you're observing an electron, light interferes with its wave property?
Yeah, it collapses the wave function.
Okay.
In order to observe anything in nature, like anything on the quantum level, you have to interact with it in order to define it. So like, yeah. So this like brings up like kind of like a concept talk really deeply in the Tao physics, yeah.
Is this like the commonly accepted paradigm? Because I thought that
what?
commonly accepted paradigm, scientific paradigm, because I thought there's still a point of high contention.
The measurement problem is still under debate. What exactly is happening to the probability field when it's being observed?
Are they sure that it was, how do they know that it wasn't just like the instrument they were using to observe it? Rather than themselves?
Rather than their consciousness?
Yeah.
Yeah, I'm just pretty sure that it was they needed light to observe the electron, and I don't think if people like thought it would change.
Well, wasn't it? I thought that it was detected by. It wasn't detected on like a copper sheet or something like that.
Yeah, that's where the interference pattern. That's where this pattern comes up on. So basically, like, look. So if you have a wave, right, it's going to make it like an interference pattern, right? But then if you're like, okay, which one does it really go through? So like when you have light, basically what happens is you collapse the wave to this point. So then it's just like the wave, it's still a wave, but it just goes through one. So it just produces one. It can't go through both. But isn't that really interesting? Like, so you shine an electron and like it interferes with itself. The probability field interferes with itself. That's like so amazing. So this is like, yeah, this.
So it was actually more to do with the, like, the equipment, like the fact that you had